Hello and welcome to this video. Today I will show you how to code the simplest machine learning algorithm called Perceptron. Perceptron consists in a single neural machine learning model capable of doing linear classifications. In this example, we'll be using the famous iris dataset that we can plot here. And this set consists on two types of flowers. We can see one here in red and the other group is here in green. Since these two groups can be separated by a straight line, our perception model should be able to solve this classification problem. Also, we will be analyzing the evolution of the model. Here we have a decision boundary plot for a randomly initialized perceptron, and we will be able to see the evolution of the model as the model gets more and more training. At the end of the video, we'll be able to see the evolution for a model trained 100 times. So let's get started. First of all, we need to import these three libraries, NumPy, Pandas, and Matplotlib. Then we need to import the CSV file from this URL and convert it to a Pandas data frame. We show this data frame, we will see this composed by 150 rows, and even though you can see it, this has three classes of plants. The first 50 rows contains Iris setosa plants, the next 50 rows contains Iris versicolor flowers, and the last 50 rows contains Iris virginica flowers. So, since our perceptron model is only capable of doing binary linear classifications, we have to get rid of one of these classes. So, by slicing the model like this, we are getting rid of Iris virginica classes, and as we can see, our final data frame consists of 100 rows and only these two classes, setosa and versicolor. If I make a plot with sepal length as x-axis and petal length as y-axis, we were able to see the plot as showed you at the beginning of the video. Okay. And here we are doing the data preparation. Okay, but we are going to talk about this a little bit later, after we have understood how the perceptron works. Okay. Here we have a simplification of our perceptron model. Okay. The main thing is that this perceptron receives two inputs, multiplies them by randomly initialized weights, adds to this a bias, this corresponds to this equation, and we obtain this output here that is called summation. Okay. Then we have to activate this summation with this sigmoid function we can see here, and what is going to do this function is to convert every output here into a 0 to 1 value. So after the summation is activated, we get our activation value, or what is the same, the set, that is the actual output of this model. And then we are able to calculate the error. That is the difference between the expected output and the actual output. Okay, so as we said, the weights and the bias are randomly initialized at first. So the output we are going to obtain at the first times are going to be random. So the model has to adjust itself in order to fit to the real outputs. So this process of adjusting the weights is called backpropagation. Okay. The velocity of backpropagation depends on these parameters: the confidence inverse, the error, and the learning rate. Okay. To understand the confidence inverse, first we need to realize that our final inputs are gonna be 0 or 1, okay, or expected ones. because 0 corresponds to one class of flowers and 1 with the another class. So everything within these two values will be a bad output. So if for example our summation value is 0, our final output will be 0.5. So our model is not confident at all of what classes of these two should be. Okay, so this confidence inverse value is calculated with this function here, that is the derivative function of the sigmoid. Okay, and we get the higher values for close to 0 summation values. Okay, once we have calculated the confidence inverse, we are able to calculate the weighted error, that is the error itself, the error we saw here, plus the confidence inverse. And this learning rate, okay, is a value that we determine at first and we could adjust in the future if the model is not behaving as we expect. So for weight adjustment, we add this product. Here we have the inputs, the weighted error, and the learning rate. Okay, so that's the main thing. This process of learning is gonna happen over and over until our error is close to 0. Going again with the inputs, we are gonna define our inputs in this X matrix. It has two columns. One column we will have the sepal length, and another column we have the petal length. And we will define the expected outputs in this column matrix called Y, and also we are gonna convert its values to 0 or 1. Okay. Iris setosa classes are gonna be converted to 0 and iris versicolor to 1. So we execute this cell, and here is the code for the Perceptron class. The main thing happens here, the train function. Okay, this function receives as parameters the input values, the expected values or the expected outputs, the number of times the process of learning is gonna be repeated, and the learning rate. So the first of all, we have to define our weights and bias. Weights and bias typically get the values from -1 to 1, but in this case I am gonna do this adjustment. Okay, why? Because our input values, as we can see here, come from 4 to 7, and these are very high values. So this is gonna, when we calculate the summation, we are gonna be close to this part of the function. So our confidence inverse is gonna be very low. That's gonna make our weighted error be very low as well. So this adjustment that we are making to the weights is gonna be very low, so our weights are gonna be frozen. So our model is not gonna learn at all. So the better practice is to modify the inputs and set them between 0 and 1. But to make things simpler, we are gonna do this adjustment to the weights and the bias. And here is the for loop for learning. That's the way the model learns. First, we calculate the actual output. Then we are able to calculate the error. After, we calculate the weighted error. And now we are able to adjust weights and bias. And after all this is done, we store the historic of the weights and the error in order to be able to plot this evolution a little bit later. So here, what we're gonna do, we are gonna create a Perceptron object and we are gonna train itself. So for the training, we define these parameters, number of iteration as 100 and learning rate as 0.3. Okay, this parameter we are gonna modify to 20 actually, and if I execute the cell, the Perceptron has been trained. So now I am able to plot the evolution of the weights and the error here. Here is for the iteration 0, and we can see how this weight is getting closer and closer to 0 as the training process is repeated. If I set the number of iterations to 100, I will have this model with an error almost fitted to 0. Okay. And here we have a formula for plotting decision boundaries. I execute the cell. And in this cell we are going to use that formula for plotting the Perceptron model. Okay. As you can see, the model is very fit. Okay, the red area means that if I give the model an input within this area, it's gonna be classified as setosa flower. Otherwise, if I give the model an input within the blue area, it's gonna be classified as versicolor flower. So the model seems to be working fine. And I found very interesting to be able to see the evolution of the model decision boundary. So I'm gonna set the learning rate to 0.1 in order this model learns slower. If I go to this folder, I see how these plots are being actualized. Okay, so now we're going to be able to see the evolution of this model. You can see here the number of iterations, 0, is the randomly initialized model. So here there has been no learn. So you can see the decision boundary is upside down. So the error is 100%. So if we go to further iterations, we see how the model gets better fitted. So that's all. Hope you enjoyed the video. Feel free to download the code, try it by yourself, and have a nice day. Bye.